So, at this point, I'd like to introduce the next speaker. Sébastien Hilaire obtained his PhD in computer science from the French National Institute of Applied Science in 2010, during which he focused on using gaze tracking to visually enhance virtual reality user experience. After Dynamics XYZ and Criterion Games, he joined the Frostbite team as a rendering engineer. You can find him pushing the visual quality of the Frostbite engine in many areas such as volumetric rendering, visual effects, or post effects. Okay.
Just play it. F5. Okay. Hello, everyone. Pleasure to be here. So I'm Sébastien Hilaire, a rendering engineer at Frostbite, and I'm here to present to you our latest work on physically based and unified volumetric rendering. So just to give you a bit of context first, last year we moved Frostbite to be a physically based rendering engine. You can refer to last year's presentation from Lagarde and Deroussier if you want all the details. And this resulted in a huge increase in visual quality. You can see 2 screenshots from Need for Speed, and it's hard to tell which one is from the engine, which one is from the real life. But next to that, volumetric rendering in Frostbite was very limited at the time. We had global distance and 8 fog, screen space, light shaft, and particles. And we wanted more. Nothing wrong with these techniques, but we wanted more. We wanted, for example, atmosphere simulation, sky, large-scale fog that could have varying densities, scattering events, scattering occlusions also to get some sort of light shafts. So there are a lot of techniques that allows us to do that. There's some billboards, you can use billboards, there's analytic fog, analytic light scattering. You can use screen space light shaft with post-process, or if you want a bit higher quality, you can use epipolar sampling. More recently, there's been splatting method being used a lot, so you can splat your light volume, for example, or just some simple spheres to give color to your scene, some volumes. But these techniques are often very limited because you basically just say it's not physically based first, and also you don't have the varying density you will expect for some large-scale fog, for example. You will want varying density heterogeneous participating media. But more recently, Wronski presented volumetric fog last year, where you could have all your participating media voxelized in clip space, and then compute interactions with the local lights and the sun with shadows. And it was supporting, of course, heterogeneous media. And that at the time when we saw that work, we were very happy to see that because we were doing the same thing, basically. So it's good to see that someone is doing the same kind of work. So it's a valid approach, we think. So our motivation and scope, so we want, of course, increase the visual quality and give more freedom to the game teams for them to increase the complexity of their visual and a different mood for their scene. They may want different overall ambient and mood. And we want our volumetric to be physically based for several reasons. The first is, so we want to have meaningful set of parameters that artists can author. We want to decouple the material and the lighting, so we don't want scattering color on the lights, for example, that's wrong. And with this, we should get coherent results that are easy to understand and improve on. And we want everything to be unified also. We don't want factorial n technique when you have n different things that needs to interact together. For example, you have particles, opaque, participating media, transparent. We don't want to have different techniques for all the different interactions when it comes to lighting or shadows. So this is the result we have in Frostbite. So this is a thing with very thick fog, and without volumetric it looks a bit flat. But when you enable volumetric, then you can see the shadows moving, you can see where are the lights in space. This is another scene showing a local fog volume. You can place them in the world, and with volumetric shadows is cast on opaque. The participating media is self-shadowing also. You can move the lights also, you can move the participating media, all this can be dynamic. So this is the outline of my presentation. We just present first how we achieve volumetric rendering in Frostbite. Then I will present how we achieve volumetric shadows. And then a few more goodies if I have time before I conclude. So volumetric rendering in Frostbite, we restrict ourselves to single scattering. It's already hard enough. So what happens? How do you compute that? So when you have a light interacting with a surface, you can evaluate the BRDF, and then you get the the final light incoming on the camera. But if you have participating media, then it's a bit more complex. You need to take into account the transmittance toward the camera, so light will be absorbed and attenuated. And also you need to take into account scattering. So for each of the samples you have, you need to sample the incoming lights. You have to apply the transmittance for each of these points. It's going to be different. Also, you need to take into account phase function. If you have a phase function, it could be isotropic participating media or anything. And of course, the last one is take into account the shadow maps, so occlusion. So you could use shadow maps or volumetric shadow maps to evaluate this. So in our case, we use the same approach as Vronsky. Everything will be done in clip space on frustum-aligned 3D textures. So that is important to understand for the full presentation. And just as a note, Frostbite is a tile deferred lighting engine. So for each lighting tile we have, which are 16 by 16, we have a cut light list for opaque, so between near and far depth for the tile, and also between for forward transparent objects between near camera plane and the far depth. So this is important because we want to reuse this light list when we compute the participating media interactions, because these light lists are curled, of course. And by default, we go 16 by 16, and you can go into finer grain volumetric tile in screen space. And you need to be careful with resolution integer division to align the tile. So this is an overview of the data flow we have. First, we need to voxelize all our participating media entities into the clip space volume. Then from these material properties and all the light in our scene, we can evaluate scattered light for each voxel, and then we can integrate everything to the final buffer that will be applied in our scene. So let's have a look first how we define our participating media. So each participating media will be defined according to the physically based theory, for example, using absorption that reduces the amount of light when traveling through the media, scattering that will make light bounce on the media, the phase function, which will give a different shape of because the light can bounce more forward or can bounce uniformly in the media. You can also have emissive if you want some sort of toxic waste or I don't know, any other thing. And a few more parameters that are important, like extinction and albedo. So this is important because artists, they will author emissive phase function, and then they can author either absorption scattering or albedo extinction. And this is basically albedo extinction is a bit more intuitive for artists because it's just a color and a way to say this is how the light is going to attenuate. So train your artists because it's important for them to understand all these parameters, as all physically based parameters, I would say. So once we have that, we can voxelize all our participating media source. So we have the depth fog and height fog we can voxelize, and also local fog volumes. As you can see, these are just cubes with uniform participating media into them. And you can make a variation according to a density texture to give them a sphere shape or noise shape. And all of them has voxelized into what we call the V buffer, which is analogous to the G buffer, but in volumes with all the participating media properties. So we just accumulate all the linear parameters, for example, the scattering, emissive, and extinction. We take into account the phase function, but we only have one lobe, so for that we have to take the average. And you can see that we are using wavelength-independent extinction. This is because it's practical for now. It will be easy to change if we want in the future. So now that we have all our material properties in clip space, we want to use all the lighting information of our scene to evaluate the scattered light per voxel for each of the voxels in clip space again. So this is the buffer we want to compute at the end. And for that, we just take one sample per voxel and integrate all our light sources, which are indirect light, sun, and local lights. So this is as seen with participating media, but you can't see any scattering yet. And then this is when you take into account indirect lights. So this in Frostbite we have like ambient diffuse spherical harmonic light probes we can sample in space. So we just take one sample at the center of the volume. For now, that's enough. And if you have a phase function, varying phase function, you can use the spherical harmonic cosine lobe trick presented last year by Vronsky. Or you can also have the sunlight. So this, you just get basically sun scattering from the sunlight, and you can sample your cascaded shadow map to have like volumetric shadows, as you would expect. For the local lights, so you can see I've added a few local fog here, local lights in green here. We just read all the lights in the tile light list that correspond to the volumetric tile, and basically just integrate all of them. And if there's no scattering properties on your voxel, you can skip early out. And for each of these lights, you can take into account shadows, so that helps to localize the light better. And also volumetric shadows. So you can see participating media is self-shadowing, and it prevents the light from going through them in other areas. And you have an overall participating media. I don't know if you see it. That's a bit noisy also here. And it gets shadows also properly. So I will describe them later. The volumetric shadow maps, I will describe that later. Just assume it's there for now. So if we take just one sample per voxel, then aliasing starts to appear. You can see undersampling here. So the depth slices are visible, the light is flickering, the participating media is very thick, so it's only in that case that you can see the flickering. And shadows make it worse. So if you can look at this scene, you can see the shadows from the tree. They will flicker a lot when the light is moving, and same for the lights at the bottom of the scene. So what we do is, as everyone, we are going to temporally integrate everything. So for each sample we take, so for the scattering light sample and the material sample also, we are going to offset all of these samples on the camera view direction. And so you need to have the material and the scattered light sample in sync. They should have the same offset. And so to filter that we filter that with the previous frame. We just basically take a 5% blend with an exponentially moving average as Caris proposed for Temporal A last year. And we skip history if it's out of first run. So this solves a lot of problems. So you can see that's before the temporal integration, and then once you enable it, you basically have everything fixed. And same for this scene, the volumetric shadows from the trees, they all look soft. You can still see them moving, and the lights on the ground are no longer flickering also when you move. So this is still an improvement, but not good enough, I think. What do you do when you have animated participating media moving in the scene? This one will leave trails. So you could reproject using the velocity of the participating media if you would voxelize the velocity, but what about multiple volumes that intersects? And what about animated volume, like fluid simulation or smoke simulation that we want to have also? And lights also will leave trails. We could use neighbor clamping as Caris proposed for Temporal A, but that won't be enough. So this is something we have not solved yet. So this is a challenging research area for the future. So once we have all our scattered light evaluated per voxel as well as extinction, we can basically integrate them for each of the view rays on the first term, to basically have for each voxel the scattered light and transmittance toward the camera. So this can be just done iteratively, slices by slices. So for a voxel, you just sample you attenuate the scattered light by the previous transmittance, and then you attenuate the transmittance, you accumulate the transmittance for the next voxel. So you could think that this could be a good approach, but in fact, so that's the first thing we tried first, but this is wrong. Because you have a dependency on the absorption. So should you accumulate first extinction and combine transmittance, or is it the opposite? So in fact, this is wrong because also it's not energy conservative. If you have highly scattering participating media, you will just emit more light than necessary. So you could think, okay, let's swap, let's accumulate transmittance first and then scattering. But then you will have completely dark materials. Even though you get back your albedo, you will expect it's just completely dark, and temporal A will never be able to solve that. Temporal sampling, I mean. So we can't do anything. We can't do a lot about the scattered light sample. But what is going wrong in this case, in fact, is that we consider that the transmittance is constant for each depth slices. And this is the problem, because transmittance should be 0 at the start of the depth slice and should be what it should be according to extinction at the end of the depth slice. So what we do instead is temporally integrating analytically the scattered light as a function of transmittance, using this simple formula, and that just solves the problem. So this is without volumetric shadows. You can see you get back the albedo. It's at the correct intensity level you will expect. And this solved also, we were having some light bleeding with volumetric shadows for very still participating media volume, and this fixes also all the problems we had in that case. So very important to have this. Okay, so once you have integrated your volume and your final solution, you have basically per voxel scattered like the transmittance, and you can simply apply that on your scene as pre-multiplied color alpha. It's as simple as that. You can see this on this scene. You have some particles and some local fog volumes. And if you lock the view and look from another point of view, you can see the participating media, how it's applied on the scene and how it's applied on the particles also. So of course, because we went for physically based, we wanted to compare our results with a physically based path tracer to make sure that, okay, we are correct. So we compared again Mitsuba, and with the same condition, so single scattering and only same exposure and all that. So the first thing I'm going to show you is a view of a plane with a thick layer of participating media, and the light will be first on top and then inside. So this is the result, basically Frostbite render on top and Mitsuba under. And you can see that it really matches, and also you can notice that we recover the kind of cone shape of when the light is inside the participating media. There is a bit of a difference, though, and this is due to the fact that we discretize the participating media and the volumetric shadows, as I will show later, into voxel. So this is the approximation that caused these small changes. Same another scene, uniform large-scale participating media with uniform scattering, uniform phase function, and then strongly forward phase function. Okay, let's talk performance a bit. So I'm going to give the performance for the sunlight for this scene with the sunlight. There's 14 point lights, two of them with regular and volumetric shadows, and 6 local fog volume with density textures. And this is the result on PS4 at 900p with 64 depth slices. So you can see that the most expensive, of course, is the light scattering evaluation because of the local light. So for 8x8 pixel tile, volumetric tiles, you get sub 3 milliseconds for that scene. But if you go for 16x16, you get like sub 0.9 millisecond. And this is a breakdown of the light scattering components. So local light is really the most expensive one. This is something, we have optimized it a bit, but there's more things we can do also. And this really tells something that is important, is plan ahead for your use case. Do you really want 8x8 tiles with local shadows? Do you want really high frequency shadows? Then maybe you should go 8x8. Maybe that's what's needed when you do a very, very high quality interior scene. But if you go outside, maybe you want 16x16 tiles, and maybe someone just wants ambient fog volume somewhere, not necessarily all the lights to be voxelized, to cast scattering light. Okay, so now I'm going to present how we achieved volumetric shadows, but quickly also for the sake of time. So for that, we voxelize again all our participating media entities into a 3-level clip map. And this will only store extinction per voxel. And this is important to have that more large-scale volume, because you want out-of-view shadow casters also. So you can't do in clip space, that won't be enough. And then from this volume, we can generate volumetric shadow maps. For now, today, they are just 3D textures storing transmittance. And transmittance is simply evaluated by rematching the extinction volumes. And these volume textures are mapped onto the light shape. So if it's a spotlight, it would be a frustum perspective projection. And this is the result. So basically, you can see also what's important to see here is that the volumetric shadows are casted from the participating media onto opaque, onto particles, and participating media is self-shadowing also at the same time. One other advantage we have is we voxelize also our particles if we want. We can, according to 2 different quality, we could say. There's the default trilinear voxelization and a more representative sphere voxelization for each voxel that map to their size. And you can see the shadows being cascaded on the ground. And you can do also some other cool stuff, like having particles casting shadow on participating media as a function of the light in the scene, and the participating media also is applied on particles, as you would expect also. So just a few sound performance on PS4 for the volumetric shadow maps. So we have, for spotlights, for example, for 32 cube volumetric shadow maps, this is definitely cheap. You can go higher if you want, but basically for non-moving lights, 32 cubic is enough. And 1,000 particle voxelization is also very, very cheap if you go for default quality. So if you set up correctly your extinction, cascaded extinction volume, then you will get, you can get a lot of them basically. So yeah, I think I have a bit of time for 2 extra slides, 2 extra goodies we have also. So we have also, for our particles, we have a high, this is a non-unified solution. This is a specific solution for particle-sun interactions. And you can get what we're using for your opacity maps to get high-quality self-shadow and scattering on particles. So you can get like colored wavelength-dependent extinction, wavelength-dependent scattering, and also like the silver lining effect, because this is evaluated per pixel on the particles. That this can be useful for clouds or any other smoke plumes. And you also have, I can't go into the details, but that a physically based sky and atmosphere simulation. It's based on ELEC and modified. And why ELEC? Because it's a bit simpler and faster than Brinton. We don't have 4D textures, we just have 3D textures, and it still works very, very well. So once the artist has set up the atmosphere properties, scattering and all that, then they can just move the sun and get the correct sunset, sunrise, clear sky view, and all that is interactive after. And so if you know these techniques, you have to pre-compute some volume texture, and this can be distributed also over several frames if you want to, for it to be cheap, if you want your sky to be updated dynamically for time of day or weather. Okay, so what I just presented to you, the physically based volumetric conduct framework we have added in Frostbite that will be used for all our games in the future, for all EA games. So it's based on it's physically based. So by that I mean we have physically based material properties, and you have decoupled lighting and material evaluation. And we also tried, that's very important, to reduce the complexity, try to go with a more unified volumetric system. So it's applied, once we have evaluated the scattering, it's applied on everything. The volumetric shadows are also applied on everything and can be casted by everything, except transparent for now. Transparent surfaces like glasses for now. Future work, I don't have time to go through it, unfortunately, so it will be online, or you can come and talk to me. And that's it, basically. Thank you.
If you guys have a question, please come to the microphone. We have a few minutes for a question or two.
Hello. Very beautiful results, Sebastian.
Thanks.
When you voxelize, if you have participating medium on the far side of a wall, but not on the near side, how do you keep it from bleeding through in the voxelization?
Okay, so this is not handled, basically. It can go through. So you can stop the scattering with shadows, but when you voxelize participating media, it's just going to be the volume, so it will bleed through polygons, yeah. Your artist will have to end place them, like the local fog volumes, to match your room, for example.
Well, let's thank the speaker for an excellent presentation.